The next thing we're going to look at is the idea of integrating factors as it pertains to exact equations. We recall from section 2.3, we saw an integrating factor for the linear differential equation y prime plus p of xy equals to f of x. And that integrating factor, if you remember, was e to the integral of p of x dx. And that was able to allow us to take and turn the left-hand side into a total differential. What we're going to look at now is the situation where, let's suppose that we have a differential equation, and it's presented in the form we've been looking at all section long. We have m dx plus n dy equals to 0. And let's further suppose that this differential equation is non-exact. So if this is non-exact, then as it's written, the partial of m with respect to y would not be equal to the partial of n with respect to x. So what we would like to do is see, is there a way around this? Is there a way where we can still end up getting a way to solve this? And the answer is sometimes yes. And it's going to be with what's called the use of an integrating factor. So what we're going to do is, let's suppose that there's some function. And let me call that function mu of x comma y, such that if I take and multiply our differential equation, m dx plus n dy equals to 0 by that factor. So I'm just going to drop the subscripts. Again, we know that m is technically a function of x and y, and so too would n be a function of y. But I'm going to write this as mu m dx plus mu n dy, and then on the right hand side, 0 times mu would still be 0. The hope is that with this multiplication by this function mu of x comma y, will this resulting equation be exact? Okay. And we know the answer to that. Well, it'll precisely be exact if the coefficient function of dx, in this case that's not just m anymore by itself, it's the product of mu and m, we would need for the partial of that function with respect to y to be equal to the partial of the coefficient of dy with respect to x. And now that's going to be mu of n with respect to x. We have a bunch of products, so we can take the product rule. This would be the partial of u with respect to m, the partial of u with respect to y times m plus mu times the partial of m with respect to y. We would need this to be equal to, on the right hand side, the partial of x with respect to n plus mu times the partial of n with respect to x. So if we can find a function mu that satisfies this equation, then we will have our solution. The issue with this is that this is a partial differential equation, and we don't quite yet have the means to solving something like this. Okay. However, if it turns out that let's suppose that mu is a function of a single variable. So if mu wasn't a function of x and y, let's suppose that mu is simply equal to some function of x. So if mu only depends upon x, then this is how this would simplify. Well, if mu depends only upon x, then its partial with respect to y, that would be equal to 0. So we have mu of my, m doesn't change, m still depends upon y, and then this would no longer become a partial derivative. This would actually be just the single derivative, so this would be d mu dx n plus mu of nx, and now we could actually solve this for du, d mu dx would be equal to a little bit of algebra. We have mu my. I would take this term to the other side, so that would be what, minus mu nx, all divided by what? Oh, divided by n? There we go. And now, this equation is solvable. This is actually a separable ODE. So we have d mu dx is equal to, I can factor the mu out. We have my minus nx divided by n times mu. I can bring the mu to the other side. I can bring the dx to the other side. And now we can integrate to find mu. We would get that the ln of the absolute value of mu would be equal to the integral of my minus nx divided by n dx. I'm going to drop the absolute value because you just have a plus or minus sign, and then take e to both sides, and we would get that mu is going to be equal to e to the integral of my minus nx all divided by n dx. And so this would provide us with an integrating factor that would allow us to turn the differential equation into an exact differential equation. And the book kind of skips this part of the derivation, but I at least wanted to show you what it would look like. So, and that was under the assumption, so recall, that was under the assumption that mu of x comma y was a function of x alone. And that gave us the following integrating factor. Mu of x is equal to e to the integral of my minus nx all over n dx. So if you start out with an exact differential equation, this would be a non-exact differential equation of this form, compute this quantity. Compute my minus nx divided by n. If that expression ends up depending upon only the x variable, then we can use this as an integrating factor. We would multiply both sides by whatever this expression is, and that would turn our differential equation into a exact differential equation. Alternatively, and I'm not going to do this derivation, but let's suppose it's alternatively, if mu of x comma y instead is a function of y alone, so if nx minus my divided by m this time is a function of y alone, then we get the integrating factor mu of y equals e to the negative nx minus my divided by m dy. So somewhere in your notes, just make a highlight of this. So when a differential equation is not exact, we're going to look for one of these two to see if they would be our integrating factor. Let's do one of these together. So this is example 4 in the text. Let's try to solve x y dx plus 2x squared plus 3y squared minus 20. Oh boy, that's funky. There we go. Maybe not. Minus 20 dy. And let's suppose that this is equal to 0. Again, so far it looks just like every other kind of differential equation we've seen so far in section 2.4. Let's do our check for exactness. So m of x comma y would be x times y. If we take the partial of m with respect to y, that would produce x n of x comma y is 2x squared plus 3y squared minus 20. We want to take the partial of n with respect to x. That would be 4x. And when we compare the two, they're not equal to each other. So the partial of m with respect to y is not equal to the partial of n with respect to x. So it's not exact. So we can't immediately go off and try to solve this thing. So because that occurred, the next thing we would want to look for is to see if we can find an integrating factor. The first thing I'll check is to see if there exists an integrating factor of the form mu of x. Okay? And in order to check for that, what we would need is for the following thing to occur. We would need for the partial of m minus n of x, all divided by n, to be a function of x alone. Okay. Well, let's calculate this. So m of x comma y, I'm just going to use, instead of using the Leibniz notation, I'll just use the brief partial notation. The partial of m with respect to y, we just had that a moment ago, but that partial was going to be x. The partial of n with respect to x, again that means partial n, partial x, we also had that a second ago. That was 4x, and then we're going to divide that by n. So here's what we have. We would have x minus 4x all divided by 2x squared plus 3y squared minus 20, which would give us negative 3x divided by 2x squared plus 3y squared minus 20. And we look at this and we say, oh no, this is not just a simple function of x. This depends upon x, but it also has a y dependence there. So unfortunately, there will not be an integrating factor of the form mu of xy. So we have one more shot at this. Maybe it's possible that there could exist an integrating factor of the form mu of y. Okay, and let's check that. If for there to be a integrating factor of the form mu of y, what we would need would be for nx minus my divided by m to be a function of y. So we need this to be some function of y in order to get an integrating factor for this problem. I just deleted it moments ago, but the partial of this with respect to x, that would be 4x. The partial of this with respect to y, that's going to be x. And then we're going to divide this by m, which is x times y. This gives us the expression negative 3x divided by xy. The x's cancel, and look at that. We get negative 3 over y, which does depend just on y. And this is good for us because this means that we actually will have an integrating factor. And I made a mistake here on my sign. That should be a positive 3, sorry. Four minus 1 is positive 3. There we go. So we have positive 3 over y. So that means that the integrating factor for this problem is simply going to be e to the antiderivative of 3 over y dy. This is going to be equal to e times 3 the ln of y. Bring the power up. We have the ln of y cubed. And this is going to cancel, and we get y cubed. So for this problem, y cubed is going to be our integrating factor. So now what we're going to do is we're going to go back to our original differential equation, and we're going to multiply every single term on both sides by this integrating factor of y cubed. So multiply by y cubed, multiply by y cubed. On the right hand side we get 0 multiplied by y cubed, and we have the following. This is going to be x y to the 4th dx plus 2x squared y cubed plus 3y to the 5th minus 20 y cubed dy equals to 0. And the whole point of this and the claim is that this should now have turned this differential equation into an exact differential equation. Let's actually check that. So I'm going to give this a name here. This isn't the same m that we started the problem with earlier. I'm going to call this m twiddle. And m twiddle of x comma y is equal to x y to the fourth. Let's take the partial of m with respect to y, which is what we're supposed to do, if it's exact. So the partial of m with respect to y, that would be 4x y cubed. And now let's come over here and let's take a look at this function, this coefficient of dy. It's not my original n, but it's the n multiplied by that integrating factor y cubed. So I'm just going to kind of call that n twiddle. And let's take a look at the partial of this with respect to x. That's going to give us a 4x y cubed. With respect to x, this would be 0, this would be 0. And now when we look at it, hey, it is exact. The partial of this function's dx coefficient with respect to y is equal to the coefficient of its y dy term with respect to x. So now this is indeed exact. So the integrating factor worked, and now we can go through and solve it like we're used to. So what that means for us is that we know that this thing here, this thing was equal to the partial of some function with respect to x. So we can find f of xy, as we've done in the past, by simply integrating this coefficient with respect to x. If we do that, that's going to give us 1/2 x squared y to the fourth. And then, because we're integrating with respect to x, we could get some function of g, and we call it g of y. So we now know f of x up to a constant of integration g of y. We integrated with respect to x to find f. We're now going to differentiate this with respect to y. The partial of f with respect to y, this would be equal to, bring the 4 down, it's going to give us a 2x squared y cubed plus g prime of f. And recall that this should have been equal to the n tilde of x function, right? Because at the end of the day, n tilde was the partial of f, partial of f with respect to y, that is. So this expression should be equal to this part here. So that's 2x squared y cubed plus 3y to the fifth minus 20y cubed. And we now have an equation where we can solve this for g prime of y. We're going to go ahead and subtract 2x squared y cubed from both sides. Subtract 2x squared y cubed from both sides. We get the g prime of y is 3y to the fifth minus 20y cubed. And now to recover g, we just got to integrate both sides dy. Integrate both sides dy. And we get that g of y is equal to, add 1 to the power, divide by the new power. That's going to give us a 1/2 y to the sixth minus 5y to the fourth. And I'm going to save that, the constant of integration, the plus c, for the other side of the equation. So here's f of x comma y. This is 1/2 x squared y to the fourth plus g of y. G of y we now know is 1/2 y to the 6th minus 5 y to the 4th, because the differential of f was 0, we know that this was equal to a constant. And so we've successfully solved this differential equation. Our solution is 1/2 x squared y to the 4th plus 1/2 y to the 6th minus 5y to the 4th equals to C. Yay.